In the last class, we started with the assignments of this peptide MFIGL. We will now go through it and see how we can assign this peptide using 2D NOESY and TOXY spectrum as we have seen earlier. So, this is the 2D TOXY spectrum of the peptide. As you can see, we can see the correlations from NH region. This is the NH region, which is comes somewhere between 7.5, and all the way you see all the correlations to the aliphatic, that is the methyls and the methylene regions. So, this is the important region in both NOESY and TOXY that we will be using for assignments. The other region of the spectrum also has information, but that is not we are going to use for assignment purpose, that is for the sequential assignment purpose. So, first thing is that we have to identify the spin systems. So, that is what we saw in the last class, that for a given NH region. So, if I draw a line like this, I should be able to figure out what amino acid is this line corresponding to. Similarly, all the vertical lines, all the NHs corresponding to the different amino acids. So, how to identify the amino acids? It will be based on the spin pattern, the pattern of peaks for the aliphatic part, and we have seen that all the amino acids have a very characteristic peak pattern which will be useful for assignments. So, let us go through that. So, this is the region which we are going to focus on, which has all the NH, H alpha or H protons correlation. So, this is the spin system assignment is illustrated here. So, as we discussed, we go from the amide region, that is NH, and we go all the way vertical up, and then we identify the peaks and I look at and try to identify what amino acid is this particular spin system. So, in this case, this looks like a phenylalanine. We have one more AMX. So, remember we discussed this is called an AMX, but nevertheless this looks like an phenylalanine. If you go in this line, this also looks pretty much like a phenylalanine, but it could be the next amino acid, which is tyrosine. But remember, we do not know which is which right now. Although I have labeled it phenylalanine here and I have written tyrosine here, it does not mean that we have assigned it correctly. In reality, when you actually start with an unknown spectrum with a known peptide sequence, you do not know which is which. So, we will see how we can establish that identity, that this line is indeed tyrosine and this line is indeed phenylalanine. Then we look at 3 more lines, because we have 3 more amino acids, and we can see that this particular amide line corresponds to glycine, because it has only one peak, and that comes in the region of 3.5 to 4 ppm, and we from literature, from the database, we know this should be a glycine. The next line here should be a leucine. The reason being that this peak is alpha, which is not really characteristic. Alpha regions, again you should remember that they are not really characteristic, because they vary with the structure, but what is important is the beta, gamma and the methyl region. Here there is one peak which is not shown here, but it is there in the spectrum. It was at a low peak level, so it has not been seen here. So, these are the gamma peaks and delta peaks. So, this is the leucine spin system which we can assign, and this looks like a methionine, again based on the characteristic pattern of peaks which we have seen in the last class, that many amino acids, all the 20 amino acids have this characteristic pattern. So, this is how we can say that there are 5 spin systems in this molecule, and each of them corresponds to the spectrum, or each of them correspond to the pattern which we expect. But remember, again we have not assigned sequence specifically, meaning we do not know whether this is really tyrosine or phenylalanine. We have to establish that link with the neighboring amino acids, and that for that we need to go for 2D ROSY or 2D NOESY. So, this is the 2D ROSY spectrum of the peptide, and you can see that similar to what you see in TOXY, but when we look closely we will see that you get additional peaks for each line, and we have seen this in the last class where we looked at an example of alanine and leucine, where we saw that in ROSY you not only see the spin system of TOXY for a given amide. Suppose I draw a line here for a given amide, I see not only the cross peaks from TOXY, but I would also see additional peak from the previous, that is sequential I-1 amino acid. So, for example, if this line, if I draw a line here, if that correspond to some amino acid I, which I do not know what is I, but let us say some arbitrary amino acid I, then on this if I compare with toxi, I will get correlations of the same amino acid from toxi, but I will get additional peaks as well, which will be corresponding to I minus 1. So, therefore, rho-z helps to identify a dipeptide I and I minus 1. So, based on that, one can actually go from I to I minus 1, then you go from I minus 1 to I minus 2 and so on, like we saw in the last class, and that helps you to establish a link between two neighboring amino acids, and that is what is important when we want to do sequential assignments. So, let us say in this case, in this how we can do that. So, for sequential assignment, what we do is we take this H alpha amide correlation region, and this is where we will, as we saw in the last class, we can go along the backbone. We call this as a sequential backbone walk. So, we walk along the backbone, as we will see how we can do that for this peptide. So, this is shown in this particular slide here. So, what is shown here is in the red color, what the peaks in red color are coming from rho-z, and what you see in the blue color are peaks coming from toxi. So, now if you notice, suppose I again take an amide, a vertical line along this is a portion of the whole spectrum. So, this is only the H alpha, remember it is going from 3.5 to 4.5 or 5 ppm, and it is a portion of the spectrum, and this is the amide region. So, for a given amide spin system, I am seeing a blue color H alpha in toxi, which definitely now we can call it as self means its own. But along the same line, I will see an additional peak which will be sequential, means I minus 1. So, I am getting an I and I minus 1 in this spectrum for every amide. So, you can see in this case I am getting again the same, here also I am getting the same, and here also I am getting the same, and here. So, now with this information, how do I start the assignment? So, what we do is typically we start from an arbitrary spin system, whichever you like. So, let us say we start from a simple glycine, because suppose I do not know which amino acids are which peak, but glycines are easy to identify because they have characteristic single peak, and that can be starting point. So, let us say I start from the glycine. So, I have identified the glycine in my previous toxi spectrum, and that glycine is this line here, this black line, and here you can see this is the glycine peak, because there is a toxi peak also coming there. So, together means the toxi, this is the self peak. Now, if I walk along this line vertically, I see a red peak which is not there in toxi, it is only red peak here, there is no toxi peak, which means it is a sequential peak to glycine. So, now I have identified the peak H alpha, this horizontal remember is H alpha. So, I have identified the H alpha belonging to the sequential, and what is sequential to G? It is tyrosine. So, now I have got the tyrosine peak here. Now, I will walk along the same line, because along the same H alpha, and where I see a blue color peak, that will become the self of tyrosine. Remember, toxi is self. So, on that particular peak I go to rho-z, and then I walk along this line again here, and I see another peak which is not in toxi, but only in rho-z. So, that should now be the sequential peak of tyrosine, and that if I now go along the vertical line, I go to the toxi and get a blue peak, which now is a self of this sequential peak. So, what is sequential to Y? Sequential to Y is phenylalanine. So, therefore, this blue peak is a self of phenylalanine. Now, in the rho-z, I go along the vertical line again, and I see there is one I minus 1, and that could be now the sequential to phenylalanine, which is methionine. And methionine, I go now to find its amide, I go straight along this line, I see that there is a red peak here, which is here, this one, there is a toxi peak here. So, we have to go from rho-z to toxi, and in the toxi I am seeing the self of the methionine. Now, if I walk along this line up or down, I do not see anything, which means methionine is now the last amino acid the N terminal amino acid, which is correct based on this sequence. So, therefore, we can say that methionine is the last amino acid and we have gone from G to in this direction left and come up to methionine. Now, how do we identify leucine, or further if there is any other amino acid, you again start from the same glycine where we started from. Now, glycine we were looking at I minus 1, which was this, but if glycine is I minus 1 to L. So, that means at some position where L self is there, along that line I should get the peak matching with G, because for L G is I minus 1. So, that means I have to search for a vertical line in amide along the amide region such that I will see two peaks. One of course will be the self based on the toxi, but the other peak should match with the sequential H alpha, that is with glycine H alpha. So, all basically we have to do is start from the glycine amide here, this vertical line, but now go horizontal. We went vertical to go to I minus 1, but I will go horizontal to go to I plus 1. So, if I go horizontal to go to I plus 1, this is a self peak, that is the blue color of toxi, and I see that it matches with another peak here, which is there is no toxi there, it is a rosy peak. So, that has to be, now if you see in the vertical line, that has a toxi peak here. So, that means this vertical line, this amide has to be the next I plus 1 to glycine, because only then it will show the glycine as I minus 1. So, basically what is the conclusion? We can say that if I go vertically along an amide, I find I minus 1. If I go horizontally along the rosy, I get I plus 1. So, I minus 1, I plus 1. So, therefore, I got an I plus 1, and if I go vertically now here, this is the leucine peak, because for leucine glycine becomes I minus 1. Okay. So, now we can complete this walk along the backbone. So, this is like a walk along the backbone, and you can say I can start from here, go up to here, and you can see I can trace a path which is going from I to I minus 1, and it ends finally at methionine. So, this is the sequential assignment process that we normally carry out in this manner. So, once the sequence specific assignments are over, so you can see now I can say that this was tyrosine and this is phenylalanine. That information I did not have when I went to toxi. So, if you go back to toxi here, we did not know which is phenylalanine, which is toxi, which is tyrosine. This was an arbitrary assignment given, but it is verified only when we do the sequential assignment, where we actually find a link between the amino acids. So, this is the whole process of sequence specific assignment in peptides. A similar process happens in proteins, but in proteins this 2D experiment can be little messy, because let us say you have 100 amino acids, then you will get 100 such blue color and red color peaks, which becomes very complicated. Therefore, for proteins we have to go to 3-dimensional NMR experiments, which we are not going to go into this course, but the basic philosophy, the idea behind sequential assignment is basically the same, that you establish a link between amino acid I and I minus 1. Usually it is done through the amide correlations. So, now once the sequence specific resonance assignment is completed, the next process in the structure determination is to identify the secondary structures in proteins. So, remember in proteins and peptides we call this as tertiary structure, and the elements which make up the tertiary structures we call it as secondary structure. So, secondary structure is typically alpha helix, beta strands or sheets, and you have what is called turns or loops. Loops are basically a region which do not have any structure. So, we do not call them as regular secondary structure, but turns have very specific geometry. So, this kind of different parts of the protein structure have to be identified in the peptide. That means, we need to know which part of the peptide has alpha helix, which part of the peptide has beta strand, and which part of the peptide is loops, and so on. So, the example which we have taken is a very short peptide. So, in that peptide you do not expect a structure. So, therefore, we are not going to look at a real example now, but we will go through a theoretical way that how these secondary structures can be elucidated by NMR. So, that is what is written here, that before 3D structure is completed or computed, the secondary structure elements in the peptide or protein are elucidated. So, how do you do that? There are varieties of methods in NMR to do that. So, let us see go through them. So, one of the approach is to look at what is called as short distance NOEs, means short distance cross peak between two residues which are close to each other in a nosy spectrum. And typically what happens, as we will see, that in a case of alpha helix or beta sheet, they are very characteristic, like we saw the peak pattern. Similarly, there is a distance pattern between residues which are very characteristic of alpha helix or beta sheet. So, based on those kind of distance or connectivity information in a nosy spectrum, we can find out whether that portion of the peptide or protein has alpha helical nature or beta strand. So, we will see that shortly. Another approach is by hydrogen bond, that you identify the hydrogen bond pattern in peptides, and typically what will happen is the loops which are very flexible, they do not have strong hydrogen bonds, but alpha helix and beta strands have very strong hydrogen bonds. So, by looking at some hydrogen bonds pattern, we will see later on in the advanced section of this course how hydrogen deuterium exchange is done. Based on that, one can identify hydrogen bonds in the peptides regions, different regions, and that can also be very useful for finding out the secondary structure. The third is to look at chemical shift index. So, what is chemical shift index? This is called CSI method, chemical shift index. So, chemical shift index basically is following. So, once you have assigned the alpha proton, so let me go back to the nosy spectrum here. So, these blue color peaks what you are seeing are called H alpha. So, if you look at a horizontal line, this is 3.8, this is 4.3 and so on. Now, this particular chemical shift value for alpha protons depends very much on the secondary structure. So, what is done is you take a random coil peptide, for example, you take G in a peptide like XGX, where X is any amino acid. So, that in that particular peptide the glycine will be in a random coil. So, you can take a G sequence for example. Now, for each of the 20 amino acids which we have in proteins, we can look at this random coil peptides, and for each of this amino acid we can find out where the chemical shift of that amino acid will come if it is in the random coil conformation or random coil structure. So, for each of the 20 amino acids, this is done systematically by taking tripeptides X or GXG, where X is the amino acid we are interested in, and these values are actually stored in the database. So, there are several databases where you can find these values for random coil values of each amino acid. So, now what you do next is this value which you are seeing in your peptide, observed in your peptide, you subtract this minus the random coil value for that amino acid. For example, if you are looking at leucine, you subtract the H alpha of the leucine in your peptide, for example, here it is 4.23, then that is subtracted from the random coil H alpha value of leucine available in the database. So, by doing that subtraction, we generate a number, we call it as secondary shift. So, secondary shift is a word given for that value which is basically the value seen in for the peptide minus the random coil for that amino acid value for that amino acid. So, like that you can generate secondary shift for every amino acid based on the value given in the database. Now, it turns out that the secondary shift is very useful indicator of the alpha helix or beta sheet. That is why we call it secondary shift, it is a useful indicator of secondary structure. So, by looking at that secondary shift value, there is a method known as CSI, chemical shift index, which helps to find out based on the deviation of the random coil from the observed value, that is based on the secondary shift values. The method gives you an idea whether it is alpha helix or beta strand or beta sheet. So, that is a very standard approach these days for both peptides and proteins, and very useful for finding out local secondary structures. Another approach is to look at 3 bond J coupling, and this coupling is easy to measure. It is the backbone NH H alpha coupling, which helps you to find out the torsion angle. So, if you recollect in our J coupling part of this course, we saw that you can actually find out there is a relation between 3 bond J couplings and the torsion angles via the Karplus equation. So, if we see in this slide here, if you can look at this HN H alpha coupling, this 3 bonds. So, this is one bond, 2 bond and 3 bond. So, this 3 bond coupling gives you information on this torsion angle phi, and based on the value of 3 bond J coupling, you can see that the phi lies in different regions. So, if the J value which can be measured, there are different methods to ways to measure J values. One of the standard method is you just look at the doublet of this amide peak. So, we will see in the 1D. So, in the 1D, when you look at this NH peak, this peak, the proton peak, it will be split into a doublet because of J coupling to H alpha, which is 3 bonds away. So, that splitting can give you J values, and that value now indicates whether it is in alpha helical region, which is based on this angle, or depending on, and if the value is high, that is about 9 to 10 Hertz, that value tells you whether it is now in a beta sheet. So, based on this value also you can find out the secondary structure of the peptide. And now this is another way to find out secondary structure, as we saw, that is called by NOEs. So, what is NOE? So, this is what is shown here. Suppose this is an alpha helix, okay. So, it is a part of an alpha helix, the alpha helix runs like this. Now, in this I is a residue number. So, if it is an alpha helical structure, these amino acids, that is I plus 2, I plus 3, I plus 4, they come close to this residue I. So, within residue I specifically it is the alpha proton to beta proton. So, if you see the alpha proton of I to beta proton of I plus 3, alpha proton of I to beta proton of I plus 3, there is a very close distance within 5 angstrom, and that helps us to find out if there is a secondary structure is helix or not. Similarly, for helix there are some more, this is II plus 4, II plus 3, II plus 2 and so on. So, basically it is II plus 3 and II plus 4 and different alpha and amide. So, N is for amide proton. So, between alpha proton of I and amide proton of I plus 4, if the distance between them is less than 5 angstrom. And how do you know it is between less than 5? By simply looking at the Nosy spectrum, you should be able to see a chemical shift correlation between the alpha proton of I and the amide proton of I plus 4. So, such a correlation immediately tells you that these two atoms are within 5 or 6 angstroms, and if that is so, then they belong to an alpha helix, because only in an alpha helix this residues will come and take a turn and they will give you information of the secondary structure. So, these are the different information which we can see from secondary structures. Now, what we do next is to find out the tertiary structure. Tertiary structure is basically the final 3-dimensional structure, and for that you need to look at now the rosy spectrum here, and in the rosy spectrum every peak here, if you notice the spots, we call them as spots or peaks, now actually are two chemical shift correlation between two atoms, right. So, one is on the x axis, another is on the y axis. So, between the two protons they give a peak, and immediately when you see a peak, it implies that there is a distance of less than 5 to 6 angstrom between those two atoms. So, that is very important, because all the peaks here are giving you now the distance information. So, if you look at this sequence here, an arbitrary sequence, so I may see different correlations between different atoms. So, let us classify these different correlations. So, number 1 is, suppose you see a correlation between atoms in the same amino acid. So, this is alanine, and within alanine we are seeing, let us say, a correlation between H alpha to H beta, that could be somewhere in this spectrum. So, if I know the chemical shift of H beta of this alanine and H alpha of this alanine, remember there are two alanines in this sequence. So, I should know which alanine is which H alpha. So, that comes from our sequence specific resonance assignment step. So, we know now for sure this H alpha is alanine number 1 or this H beta chemical shift is alanine number 1, so on. So, once I have, suppose I see a correlation or chemical shift correlation between these two atoms in a row Z, it belongs to the same amino acid. So, we use the word intra-residue NOE. So, this is one type of distance information you will get in for different amino acids. So, in every amino acid you will have intra-residue NOEs. Now, the second is between neighboring residues. So, you see here I may get a correlation in the rho Z spectrum or no Z between this H beta atom of this amino acid, which is a serine, and H beta of alanine, which is I minus 1 to this residue. So, that type of peak which we see in the rho Z spectrum, we use the word sequential NOE. So, again you may see pairwise sequential NOE between all amino acids. So, all those will be classified as sequential NOE. A third type of NOE which you will get is slightly far away. So, this is between residues 2 to 4. So, you can see in this case it is 3 residues apart, and this is between this alanine and this serine hydrogen atom. So, the beta of alanine and beta of serine you may see or you may not see, because that depends on the 3-dimensional structure, but observing such NOEs is useful, and that type of NOEs are called as medium range NOE, because they are between two amino acids which are not far away, but in medium range. Now, the last type of NOE is known as long range NOE, and this is a very crucial type of NOE, because as you can see it is giving me information between a very far away amino acids. So, for example, this alanine may come close to this alanine because of the alpha helical or beta sheet nature or because of a turn. So, that information is obtained from a NOE between these two atoms. For example, this is just an illustration. You may also get a NOE between this atom to this atom or any combination, but if you see a distance between two atoms or cross peak chemical shift correlation between two atoms which are very far away in sequence, but they are very close, far away in sequence but close in space, and that is I minus j is more than 4, then we use the word long range NOE. So, this is a long range NOE between two atoms. Now, this is what I have shown in the linear chain. I mean, this may turn around because of its structure, but suppose this peptide continues, and let us say we have a structure like this. So, there is basically a beta strand, two beta strands connected by a loop, as you can see here. So, that is basically this whole sequence turns around and comes like this, and then these two residues come to each other close in space. So, this can happen, for example, like this in this structure shown here, where you have basically two beta strands connected by a loop to form a beta sheet, and that results in this at residue coming close to this. Now, here we may again see a correlation, chemical shift correlation between two atoms, that is beta of this and the beta alpha of or beta of this or gamma of this. So, this is for example a glutamic acid. So, I may see a correlation between this methyl to this methylene because of this structure here. The blue color you see the beta strand, and they are turning around, and these two are coming close. So, that results in a very long range distance information, and this is also very useful because now it is telling us that these two strands are coming close to each other. You may not see that information if this is a open structure. Suppose these two strands are open and they are not coming near each other, then that will not come, this correlation. So, by seeing this correlation in a NOESY, one can say that I have got a long range NOE between these two residues. So, this is what is done in from rho Z spectrum, that you have to look at all the different NOEs, and out of all of them the long range NOEs are very important. Why? Because they are the one which helps you to nail down or to figure out the real geometry or structure of the molecule. The sequential and intra-residue are definitely also useful, but they are not going to give you much information because the structure of amino acids are anyways known to us. So, a distance between these two will not change much whether it is in alpha helix or beta sheet, but what will change is the distance between this and a far away residue. So, that distance information comes from long range NOEs and that is useful. Then more the number of such NOEs which you can extract from the NOSI. So, if you see this rosy spectrum here, every peak is a information. So, the more the number of NOEs you can obtain from rosy, the more better will be the resolution of 3D structure, because that is how we determine 3D structure, by giving the inputs of these distances, which we will see in the next class. We will see how these distances can be used as inputs. Similarly, we can determine the phi angles, the torsion angles, and together they help to determine the 3-dimensional structure of the peptide or protein.